Yeah, in this talk, I'm going to be talking about how to synchronize shielded messages with fuzzy message detection. In this project, we started in the last quarter, and many people have been involved. You have the names at the bottom of the slide, and yeah, let's get it started. Let's see if this is working. Right. Okay, so the problem that we are trying to solve or to make it more efficient is how can we recover shielded messages. So this is in general in modern decentralized systems where you want to exchange some information and you want to make this exchange anonymous. There is like a very clear blueprint that it was started with Setgas to achieve these anonymous exchanges of messages, and is by the senders encrypting their messages wherever they want to send to some receiver with a key private encryption scheme, and then publish this ciphertext, which is the so-called shielded message. They publish this in a public pool, for example, a blockchain. But then the question is, since this shielded messages reveals no information at all about the identity of the receivers, then how can receivers retrieve these messages, right? This problem, for example, arises in the multi-asset shielded pool in the Namada blockchain, where when you want to implement shielded transfers, and as well in Anoma, in the Anoma protocol, when you want to synchronize shielded states or resources. So in the previous talk, Xuyan has been explaining how the shielded resources are generated. What's the encryption scheme, the hybrid encryption scheme? So we have these two possibilities. Later on, in the second part of this talk, Yulia is going to be explaining more on the Anoma particularities, but I will focus on the general statement where we have just a shielded message and we want to be able to retrieve it. Okay. So the naive solution or the free solution that comes to mind is, well, what the receivers can do. They can just download the entire set of messages from the public pool and then try to decrypt all of them to see if the content makes sense. The problem with this is that, yes, receivers needs to download the entire set of messages. So this is bad for in terms of communication overhead, and as well they need to run the trial decryption and on all the messages. Usually the ciphertexts are going to be encrypted with some public key encryption scheme, or if the encryption scheme is symmetric, then to derive the decryption key, you need to do public key operations, so that's expensive. So there is overheads in terms of computation and communication if we use a naive solution. And people have been looking at how this can be improved. There are a number of ways to do this, and one is going to be it's done using fuzzy message detection. There are other approaches like oblivious message retrieval or private signaling. Also, some ad hoc solutions in set cases implemented in some SIP, as well as there are other solutions. We focus on this one because we think is more efficient. So at the early stages of this project, we were looking at different possibilities with oblivious message retrieval, for example. But the thing is that it requires FHC in oblivious message retrieval. So the technology there is not super fast. With FMD, with fuzzy message detection, we can do it very efficiently. Also, although there are some controversies between privacy and efficiency, we can get a hold on this and leverage between get a good between privacy and efficiency, as we will see later. Okay, so what we're going to use to make this retrieval of shielded messages more efficient is fuzzy message detection. First of a primitive, a cryptographic primitive that is used to outsource detections of messages to servers that are untrusted. So we do not trust the detection server. Right. So the idea is that the sender, he generates some flags using the receiver's public key, and then in the public queue, in the public pool, in addition to the shielded message, it attaches some flag, the flag to this message, and then detect the pool, and using the detection key of the receiver detects whether the flag has been addressed, has been generated with the public key of the receiver, and that means that the message is addressed to the receiver. Okay, so in a little bit of more detail, the main point of FMD is that detection is probabilistic. So what this means is that if the flag has been generated with the public key of the receiver, and we run detection on this flag with the detection key associated to this public key, then the detection is always going to say, yes, this is a flag, it's a correct flag. So this is a true positive. But if the detection is run in a different flag that has been generated with a different public key, then sometimes the detection is going to say, yes, this is a correct flag, even if it's not. So this is a false positive. The good thing about this is that you can create the anonymity set out of this. So basically, the set of messages that are not addressed for the receiver, but output the detection outputs yes, they are addressed to the receiver, is the set of is the anonymity set of the given message. And for this to work, we need to ensure that the server, he doesn't distinguish between true and false positives, because if he can do that, then there is no anonymity set at all. So one key property for FND is detection ambiguity, and it's a security property that protects against the servers, the entrusted servers that run the detection. In summary, the important thing is that the false positive rate at which the detection is executed, if it's high, then it gives you more privacy because you have a larger anonymity set. And if it's low, then it gives you more efficiency because you filter more flags, more messages. So at the end of the day, the receiver will need to execute less decryptions. So there is this trade-off between privacy and efficiency. Okay, so this is all what I wanted to say about FMD. And now I'd like to quickly introduce the system that we've been designing in the last 3 months. So the main design criteria that we have in mind is that we want that the false positive rate that is known to a detection server, we call it the leaked rate, is high. So that means that there is more privacy towards an untrusted server. But at the same time, we want that the effective filtering rate at which receivers can get the messages is low. So there is more efficiency. They need to run less trial decryptions. At first, it seems that this is contradictory because it's not possible to set some false positive rate on the detection server, but at the same time have lower filtering rates. But this can be resolved if we move to the threshold setting. So now we are going to leverage multiple detection servers. So in this setting, these goals can be achieved. Okay, this is more or less the architecture or the overview of the solution. So in this case, in the picture, I hope you can see it well, more or less. So we have 3 detection servers in this setting. The receiver starts by generating a key pair of public and secret keys. The public key is just publicized, so every sender can use it to flag messages. And then the secret key is passed through multi-extract algorithms that generates the detection key for the different servers. Once the servers get the detection keys, they can start filtering messages and then send their outputs back to the receivers, who is going to combine all these filterings and run the trial decryption on the combination of these filterings. So the key parts, or the parts that uh, are novel in our solution, is the multi-key extraction and the combined operations. Both are run in the receiver side. So I'm going just to explain quickly about how these two components work. So for the multi-key extraction, as I said here, in the standard FMD, in a standard FMD scheme, there is just one single detection key. So from a secret key, you extract one detection key. We generalize this to, from a single secret key, we can extract multi detection keys, as well as, instead of passing just one rate at which the detection key is going to be able to filter, we pass two rates. One is the leaked rate and the other one is the filtering rate. The requirement here is that any coalition of no more than T servers, where T is a parameter as well that is passed to the multi-extract algorithm, can infer any information at all about the other detection keys that they do not control. So this means that they cannot, that you can put a lower bound on the filtering, on the filterability of this coalition of these servers. So this is a generalization that we described with respect to the syntax and the semantics of the FMD scheme that appears in the original paper. And we build a scheme just by doing very, very minor modifications to the FMD2 scheme that is present in that paper. The other operation that is important is the filter combine. So now the receivers, once they get all the filterings from the different detection servers, the idea is that the receiver is able to combine all these messages somehow. And then the output of this combination, it looks like as an output that was filtered at a lower rate. So it's at a rate PF, which is also the other input that we give to the multi-extract algorithm. So these two rates are decided by the receiver and are chosen, and it gives you this balance between privacy, where the leaked rate is what is known to the servers, and the filtering rate is known to the only to the what is achieved only by receivers. One important thing to note here is that the combination, the combined operation is public, so everyone can do it. It's efficient, and that's nice. I mean, that's what we want. Otherwise, it wouldn't be important. But it's everyone can do it, so there is no secret information involved when you combine, when the receivers combine. And this means that we need to be careful and protect what is sent between servers and receivers, because anyone getting that information can filter at lower rates as well, and lower than anonymity set. Okay, so these are the two core components of the system, but we also look at three different nice to have features that we can also implement and actually are implementing. So one is key expansion, the other is key randomization, and the other one is doing key rotation on the server side. So for key expansion, the thing is that the scheme that we are using, the FMD2 scheme that we are basing our solution, it has public keys that are too large, are very large. The question is, how can we make these keys shorter? There is a challenge, which is public derivation. So if we make the public keys short and send these public keys to senders, they need to be able to later expand these keys into a fully fledged FMD public key. So this derivation must be public because the senders, they do not have the secret keys. And these two combinations is what makes things a little bit challenging. So one approach would be using BIP32 like ideas, in which actually there exists work on this. The idea here is that you start with a set of master key pairs, and then you take linear combinations on the secret key pairs to derive the keys. That's fine. We could do that. We are not doing it this way, but that's one possibility. Okay, so that's one of the features that we can implement, key expansion. The other one is key randomization. So here the idea is similar to stealth addresses, in which you are able to randomize. If you can randomize the FMD public key, then the receivers can emulate different identities. So for each randomized public key, there is one identity. But at the same time, we want all these identities, all these public keys, to be controlled by the same secret key, which means it's also controlled by the same detection keys given to the servers. So this is good because it simplifies the life cycle of the detection keys, and also I think it has a good impact on privacy, because at least for the notion of unlinkability of it helps to avoid trying to link messages that are sent to the same entity. And the last feature is server-side key rotation. So here it is important for forward privacy. So in principle, users, I'm just kind of rushing because I think I'm running out of time. So for server-side key rotation, the idea is that the users, they rotate their detection keys with the servers, but they might forget to do it. So ideally, should be the servers who can, do this key rotation on the background, and they can do it without any action from the user. The idea here to achieve this is that flags for messages are generated using an extra FND public key, which is owned by the detection server or servers. So if this is possible, then it's only needed to rotate the detection keys owned by the detection servers. We still have detection keys for users, but there is one extra detection key that is only controlled by servers, and that's what is being rotated. And once these detection keys are erased, of course, at some moment in the future, if this server is corrupted, then it won't be able to find identities of messages from the past. So that's why it's interesting. Yeah, I hopefully did not rush too much. This is all I wanted to say. I'm going to pass the control to Yulia, and at the end of her presentation, there will be time for questions. So I will be as well available for that. Thank you.
All right, now we will start part 2 of the shielded state synchronization presentation, in which we will introduce tea. Over to Yulia.
Yeah, so I'm going to first talk about how to expand this solution to Anoma, and then about teas. So the need to extend this protocol for Anoma is because Namada and Anoma are kind of different. And Namada supports simple transfers, where a sender just sends something to the receiver, and Anoma supports programmable transfers, where there is a solver. And solver makes everything complicated, and specifically it makes us need to have a verifiable FMD. So just to explain why in more details, here is a diagram. So there is a sender. Sender wants to send something to the receiver in an encrypted form, and the receiver has the key, but the receiver doesn't know what to decrypt. So what the receiver naturally would do is to try to decrypt everything, which is not exactly efficient. When the receiver realizes that, it becomes very sad. So the solution would be to have an FMD server and to augment transactions with some flag ciphertext. And the server just tries to decrypt the ciphertext that tells if it's designed to be received by the receiver or not, and then forwards everything to the receiver, and the receiver just enjoys the results. So this is how it is for Namada. But for Anoma, we have a solver in between. So the sender asks the solver to do something, and the solver, in principle, is not incentivized to send exactly what the sender wants. So here the sender wants to send a love letter, but solver decides to send something else and just throw the love in the trash. And in the end, the receiver is very sad because the receiver doesn't receive the love letter and everything is sad. So to fix that, we need to add additional field to the transaction that proves that what the solver did is actually correct, that the solver encrypted the flag ciphertext correctly and the transaction is correct and the receiver receives the love letter and everyone is happy. And yeah. So this is how we extend FMD to work with Anoma, verifiable FMD. And to make it even cooler, we add TEs. We add TEs to FMD server for both Namada and Anoma, so it's not specific to Anoma case. I just didn't want to change the diagram. So what is TE? It's a hardware solution for isolated code execution. And it allows to protect against malicious host environment. So in case you send your sensitive data to someone you don't exactly trust, TE can help. And it's supposed to provide confidentiality and integrity. So for confidentiality, we need to keep detection keys secret from the host. Detection keys are used to determine if the transaction is for the receiver or not. Then we also would like to keep the detected messages secret from the host. And generally, we would like to keep secret everything from the host if we can. Some things we can't, but ideally as much as we can. And integrity allows us to make sure that the FMD protocol is running correctly, so that we are running the protocol we are saying we are running. And so you might have heard about TEs and heard that they might be not exactly secure. And there are some attacks on TEs, and they work more or less similarly. So they leak data from shared memory, like cache, or from controller-related memory, or via hyperthreading, and can leak both application-specific data, so the data that we share with the server, and also TE keys, so the keys that make the solution secure against the malicious actor. And leaking these keys allows to break integrity of the TE. And this pattern is kind of similar for all TEs that we checked, namely SGX, TDX, and AMD SEV. Yeah, I mean, with details changing. But if we analyze attacks in terms of what we can do about them, we can divide them into two categories. Some attacks that can be mitigated by developers, which we don't care much about because we can mitigate against them. And then there are attacks that require microcode update. And this is much worse because it requires the TE developers to update the firmware, which is super slow, and we're depending on someone else, right? And this will always probably be the case because it's a hardware solution, so we're always dependent on who develops the hardware and firmware. And so microcode update requiring attacks can be divided into the ones that require kernel mode access, so the operating system privileges, or user mode. Luckily, most of the attacks do not work in user mode, so if the attack works in user mode, it kind of means that anyone can do that who has access to the same machine. So if we assume that the operating system is not malicious, then we can mitigate against all of the attacks, all of the kernel level access attacks. So the thing here is that the most relevant attacks require the operating system to be malicious, the attacks we want to protect the most from. But at the same time, TEs are kind of designed to protect against that, right? So like if operating system is malicious, then TE is supposed to help, but the attacks, well, you see. So what we do, we assume that the operating system is not malicious, and therefore we automatically protect against most of the attacks within our model. Of course, in reality, it's not exactly like that, so if the operating system is malicious, all of the guarantees that we have in our model do not apply. So the question is, do teas actually help then? And the answer would be yes, because teas increase the cost of the attack. So it's similar to having a lock on your diary. Maybe if it's not locked, someone might read it just for fun. But if it's locked, it's just not worth it, unfortunately. Yeah. So there are more challenges with teas that we have, namely reproducible builds, tooling, availability of teas, and because of all of that, reduced practical integrity benefits. So in details, the way integrity check works in teas is basically it's a signature over the tea state, and for that you need a binary of your application. It's included in the state, right? So it implies that whoever verifies the signature compiles the application from the source code and then checks the signature against this compiled binary. And this kind of assumes that compilation works the same way on different machines at different times and possibly on different settings. And this might not be true, especially for TEs. And this is related to the second issue, that the tooling you need for TEs is not very mature. And you basically need to develop your own things for more or less everything. And because of that, well, not because of that. So like some of the TEs are based on virtual machines, for example. And because of that, you kind of need to develop the whole thing yourself, because you need to integrate your application in it in a way that is just inconvenient. So right now it's not super mature. Another issue is that availability. So cloud providers support access to TEs, but the providers I checked, they support a limited number of TEs, some of which are custom and might not be so interesting to us, for example. And they also provide limited access to these TEs, so proper testing is not even possible. But like, we can get our own servers to test. Obviously, one server per TE, because we can probably have different TEs on the same server. But the problem is that we're not going to be running this. This will be run by some other computationally powerful entities, right? And they will have the same problem. And basically, depending, like, if they go with cloud provider option, they have limited access to TE. If they go with their own servers, then they might have different servers, different TEs, and so we need to make application work for multiple TEs, but we know that tooling is problematic, so we need different tools for different TEs, and different entities use different TEs, so it's like, it's a lot. And because of all of that, we have actually reduced practical integrity benefits, because it's all a little bit annoying, and nobody wants to put their code in the whole TE. For example, we have the whole FMD protocol, and if we put it in the TE, then we get guarantees about the whole FMD protocol, right? But it's extremely complicated, because we need to interact with the indexer, and it's just difficult to do from the TE. And so we put the detection part of the protocol in the TE, but then we basically only get confidentiality for the detection keys and integrity for the detection part. But we do still communicate with the operating system, against which we would like to have protection and integrity guarantees, which are not provided if the operating system runs the protocol. So yeah, there are a lot of problems. On this optimistic note, I would like to hear your questions. We are about to release a report. It's currently in review. We also want to produce an academic paper with enhancements that Enrique mentioned, and security analysis and benchmarks. And we also have a prototype on GitHub, and we have a bunch of posts on Research Forum that discusses all of that. Now I'm ready for the questions.
All right, thank you, Yulia. Questions from the live audience? Yes, Jamie.
Testing. It's work. Okay. Yulia, thank you very much for that lovely talk. I have two questions. One is, just to be clear, are teas worth it? And the second question is, I once went to a talk on teas, and I remember the speaker said it's useful to get different teas to talk with one another. So he said similar things to you, that the friction is if you want to communicate between the outside world and inside the tea, but if you can encapsulate everything in different teas, then they can communicate via confidential channels. So I was wondering if, presumably you've considered that, but you didn't mention it, so how does that fit in? That concludes my questions.
Yeah, so I'll answer the second question first, because it's less philosophical. So yes, it is easier to make teas communicate to each other, but the problem is that we want users communicate to FMD server. So if we use teas communicating to each other, it means that users have to have access to teas. And so the question would be, do they have their own tea, or do they use cloud provider, or like how does it work? So it's like basically we want to make it easier for the user, and if we make the user to use teas in order to make it easier, it might result in the opposite result.
Thank you.
Yeah.
And when I asked if teas are worth it, I didn't mean it philosophically, I just mean, are they worth a bother?
I know. I thought about it. I expected this question, honestly, and this is not exactly a theoretical question, I think, because we have another problem that we try to solve with teas called private solving. So just a short introduction. Private solving is about solving intents in a way that the solver doesn't see what the intents are. And so we came up with the conclusion that teas are probably the most viable option. And right now, I don't think so, honestly. So teas were the most viable option compared to MPC because it's easier to use, but now it doesn't seem that way. So if we put a solving strategy, for example, in T, we cannot put the whole strategy because it's even more complicated than the FMD protocol. FMD protocol is quite simple compared to that. So I don't think T will give us that much benefit, and I'm not sure what to use instead, to be honest. So I'm definitely not feeling as positive as before about T's, to be honest. But maybe with advancements in tooling and availability and like increased popularity, it gets better. But I feel a bit skeptical about the whole microcode update situation because I don't think it will go away ever.
Other questions from the studio audience? Isaac.
Thank you. I'm curious about alternatives to fuzzy message detection, especially if we're willing to make the same kind of threshold assumption that one of our intervening servers from someone in this group is honest. Are there other private information retrieval techniques that we could consider?
I think so. I think there are other techniques that we can consider. I think fuzzy message detection is the most promising in that sense. But one thing that we were discussing on the forum is something that Chris proposed as shielded state synchronization that is, I think, push-based or pull-based. Yeah, push-based. So basically where the receiver is kind of notified about receiving something via mixnet, so you basically always know what to decrypt. So instead of trying to decrypt everything or like delegating it to someone, you kind of get to know what to decrypt. But I think other solutions similar to FMD are not that kind of helpful.
Other questions from the live audience? Any internet questions? Okay. Then thank you again, Yulia and Kike.